So let's take a look at this problem. If we're asked to find the derivative of y is equal to e to the sine 2x plus sine e to the 2x. So looking at this problem, I don't have multiplication between my two functions, so I'm not going to really use the product rule for this problem, but what I can see is that I have a composite of a couple different functions. So when you see a composite of functions, which means that basically you have a function inside of another function. And the way that we can identify this is if we're looking at what we usually would have is e to the x, and we can call this our f of x. This would be our normal function for f of x, e to the x. But then if we have another function called g of x, and that's our sine of 2x, well, then we have f of g of x, right? Because if you take your e to the x, and instead of plugging in e to the x, you plug in g of x there, and our g of x is sine of 2x, then what we're seeing is that we really have a composite of a couple different functions. And then the other trick here is that if we're looking at sine of 2x, that is also technically a composite of two functions, because if our f of x is equal to sine 2x, then our g of x would be equal to 2x. So our normal function would be sine x, and then we have this 2x, but our f of x, f of g of x, and this is supposed to be just an x here, our f of g of x is equal to sine of 2x. So sine of 2x and these trig functions are actually considered composite functions themselves. And that's why when we're taking the derivative of sine of 2x, so the derivative by itself of sine of 2x, your y prime is equal to 2 cosine 2x, because you take the derivative of your outside function, which is the sine of x, and the derivative of sine of x is your cosine of x, but you keep that 2x on the inside, and then you multiply by the derivative of your inside function, and the derivative of 2x is just 2. So that's really why that 2 comes out in front for these trig functions. That's why one of the rules of trig functions is if you have sine of 2x as your derivative, then you have 2 cosine x as your answer, and then if you're finding cosine of 4x, your derivative of that would be negative 4 cosine 4x. So that's just a quick little walkthrough of what we're looking at and kind of how to identify these composite functions. So now looking at what we have here, we have e to the sine 2x, and then we also have sine of e to the 2x. So I'm going to work with these as two different equations first, and then I'm going to add the derivatives I get together, because it always helps to kind of break down problems and work with separate parts of problems if one part of the problem doesn't rely on another part of the problem. And luckily in this case, this side of e to the sine 2x does not rely on this side, sine of e to the 2x. So let's first look at e to the sine 2x. So we have one function here, which we can say is our e to the x function. And so if we want to write our e to the sine 2x similar to this, we can say that we have f of u, and we can call this e to the u. And we would have to make our u equal to sine 2x. And so now what we're going to do is we're going to take the derivative of our u, which would be 2 cosine 2x, and then the equation that we would have is that we would have our derivative of our f of u times the derivative of our u. And so now we're going to have e to our u times the derivative of our u, which is going to be equal to e to the sine of 2x times 2 cosine 2x. So this first part of our equation is going to be equal to, so our y prime for our first little part here, let's say y1 prime, is going to be equal to e to the sine 2x times 2 cosine 2x. So that's going to be that first little part here. But then looking at the second part of our equation, now we're working with a trickier part of our composite function because we're working with sine of e to the 2x. So let's first make an f. Let's call our u e to the 2x, and then we're going to take an f derivative of u times the derivative of u. And then if our f derivative of u, or our f of u itself, is equal to sine of u, then our f derivative of u is going to be equal to cosine u. And then our u derivative is 2e to the 2x. So now plugging this in, we're going to have cosine u times our derivative of u. So our y2 prime is going to be equal to cosine u times the derivative of u, which is going to be equal to cosine e to the 2x times 2e to the 2x. And so now this, and if we add these together, this is going to be both parts of our derivative. And so now writing that onto the next page, what we're going to end up with is our y prime for this problem is e to the sine 2x times cosine 2x times 2 plus cosine e to the 2x times e to the 2x times 2. That 2 can come out in front. And you can simplify this problem a little bit, but it should be fine if you look at it like this. Let me double check with what I had over here. E times 2 times e to the sine 2x, cosine 2x on the left side, 2e, yep, perfect. And then cosine e to the 2x times 2e to the 2x. Perfect. So basically what we're doing with these problems is that we're identifying a function as f of x. But then instead of just keeping this as f of x, what we do is we're going to take a substitution. And so instead of calling it f of x, I'm going to change our f of x to f of u. And then I'm going to call my u my inside function. So then my u is going to be what I'm going to substitute when I work through the problem. I substitute this e to whatever the inside function is, and I just call that inside function u while I'm working with the substitution, and then I take the derivative of that u and I multiply that times the derivative of my f derivative of u, whatever my outside function derivative is. And then it's a little bit easier if you use that u substitution for these problems, because instead of working with e to the sine of 2x, it's a little bit easier